I want to ask you something real quick. Um, we talked about the calculator in class, but would we have access to the calculator on Cengage on the test? You know how there's a built-in calculator on Cengage?
I do not know.
Yeah. We had access to that in Chem 1, the Cengage test, but I was wondering because I used that calculator for my entire test. Do we
Okay.
have access to that calculator in the test?
I actually don't know the answer though. Yeah, but maybe send me an email. I can actually forward to the CHEM1312 manager.
Okay.
He will.
You email today.
Yeah, they will know the answer.
Thank you.
Okay. So any questions before we get started? So the exam will be next week, right? I hope everybody feel prepared. If not, you still have almost 1 week to work for it. Okay. So what we are going to do today is actually to quickly go through the content that you must become a master. Okay, on the board is actually the summary that I have for the 3 chapters. This is actually all the things that you must memorize. Okay, every single thing I wrote here is critically important. Okay, so I keep making things simpler and simpler. Okay, you should do the same. Okay, so when you hit the finals, okay, which means everything will be accumulative, right? You want to have like a quick scan of all the contents that you must be memorized. Okay, this will be kind of like one of that. Okay, so we'll go through these things quickly today to cover the concept that you need to know for midterm 1. And we want to go through questions. Okay, so today we'll probably go through 8 to 9 questions, and then we'll finish the remaining one on Thursday. Okay, so when you prepare the final for the when you prepare the midterm for the next week, right? Your schedule will be something like this. Okay, during the week, trying to watch as many videos as you can, trying to internalize how I handle questions. Okay, so one thing that you guys need to practice a lot is actually read the questions. Okay, and then just do this QD pack things, right? Clearly define what the questions, what are the things that you need to actually solve. Okay, and then what's the plan that you're going to have. Every time when you read the questions, trying to identify the keywords so you know which equation that you want to use. That will save you a lot of time. Okay, so one thing you should really become a master, regardless what your major is to read the question carefully. Okay, you want to actually practice all these processes in a way that's efficient. Okay, so we've been practicing this for many weeks now. Okay, and you should get him better on that. Okay, I hope like every time you read the questions, okay, don't get panic. Okay, and then you feel like you actually go through many detours to come to realize how to handle these questions. You are overthinking. Okay, so the course is called General Chemistry, meaning things is relatively simple. If you take you several turns to get to the answer, you are thinking it wrong. Make sense? Yeah, so don't do that. Okay, so I try to actually make things as simple as I can, but I've been doing this for 10 years. Everything looks very simple to me. It's a different story for you, right? But you see how I handle things, therefore you know what's the best way to handle questions. Learn that, okay? Internalize that, okay? So on the board, you can see on the left-hand side, contains majority of the stuff, right? So let's actually your chapter 10. Okay, so chapter 10 is actually things we start to talk about solutions, right? In the beginning of the semester, we start to learn different solution terms. And one big thing over there is concentration conversion. Okay, so that's actually the very top part. Okay. So I hope by now you should actually memorize all the definitions of different concentration terms. Okay, so you have the first one is what? Molarity, right? And then normality, mole fraction, mass percent, and molality, right? So 5 different concentrations, you should know the definition. Okay. And then when we do this concentration conversion, okay, inevitably you also need to know the definition of moles, the definition of density, right? So just make sure everybody know where I'm talking about is this. Okay. So when we do this concentration conversion, one of the big thing is that we always need to make assumption. Okay, and this assumption is very simple, right? Make your denominator either equals to 1 or 100. Okay, so that's kind of the things we emphasize so many times now when we do those concentration conversion. We will only use the information of density when the concentration conversion involves molarity, the capital M. Okay, that's the only case you're going to use the information of density. Otherwise, it is just there to confuse you. Okay, so let's count like the take-home message. Okay, I assume everybody already know, okay, chapter 10. Okay, then let's actually count the take-home message I will have if I'm a student. Okay, so if you can understand, really follow what I saw, what I say today, that means actually you are more or less prepared already. Only thing remains is just practice for more questions. Okay. So after that big topic, then we start to move into the solution. We start to talk about the change of enthalpy, okay, delta H, right? So when we're trying to mix a solute with solvent, okay, then to calculate the enthalpy change of the solution, it involves 3 terms, right? Delta H solute plus delta H solvent plus delta H mixing. Okay, so delta H solute is always positive and big, okay, because you're actually breaking apart these ions from each other, okay, so it takes energy. Okay, delta H solvent is actually relatively small and not so important, okay, and delta H mixing is actually when you mix your solvent and solute together, they're going to interact, okay, so this interaction, this mixing process is typically negative and big as well, okay. And we have this name called the lattice energy for the delta H solute, hydration energy for the delta H mixing, right? So depending on the relative amplitude of the delta H solute and delta H mixing, then you should know your delta H solution could either be positive or negative. If your delta H solution is positive, we call it endothermic reaction. Okay, and the net result is actually the temperature of your solution will decrease after you mix them. Okay. In contrast, if your delta H solution is negative, that means actually the mixing is a variable process. Okay, so it's going to release heat, temperature is going to increase, right? You also need to know the relative amplitudes, right? If delta H solution is positive, that means actually your lattice energy is larger than your hydration energy. Okay, so those are the kind of key informations that you need to actually memorize. Okay, so let's actually second things that we discussed in chapter 10. Then we start to talk about the solubility, right? Meaning that if I give you 2 substance, and can you actually predict which one is actually more soluble inside aqueous solution or hydrophobic solution? Okay, so you should know like how to actually predict what is actually more soluble in aqueous solution. You need to actually looking for the molecules contains NH, OH, right? Because they can form the hydrogen bond. They will actually give you better solubility, make the molecule become hydrophilic. Okay, but if you have a molecule only contains CH halide, okay, so those are the typical atoms you're going to see for the organic compound, and those compound is hydrophobic, meaning that they don't like water. They are not going to dissolve well inside the water. Okay, so let's actually the third topic. This topic also have some more things. Okay, solubility. Okay. So solubility, temperature dependence. Okay. So if your solute is actually a solid, okay, your solvent is liquid. Okay, if you increase the temperature, solubility will increase as well. Okay. But if your solute is a gas, then the solubility will decrease, right? And the way we introduce concept is that if you heat up your Coke, all the CO2 will dissociate from your water, right? And then pressure, okay, pressure is actually only relevant when your solute is a gas molecule, okay? The higher the pressure, you're going to put more gas solute inside the solution, okay? So that behavior can be described quantitatively using the Henry's law, okay? That means the concentration of your solute will equals to Henry's law constant KH times P. P is actually the external pressure of the specific gas molecule. Okay, so these are the things that you need to actually memorize. And the very last topic of chapter 10 is the collective property. Okay, so there are actually 4 different collective properties. Okay, so the way you should understand and memorize is that here we need to actually calculate the effective concentration. Okay, when I say the effective concentration means you need to consider both Van Hoff coefficient I multiply either the molality or molarity, okay, or concentration in general. Okay, that's how you should calculate the effective concentration. Okay, and conceptually, you should know that if you have a higher effective concentration, you are going to have a lower freezing point, lower vapor pressure, higher boiling point, and higher osmotic pressure. Okay, so these things need to be actually very clear. Okay, so those are things we emphasize so many times now. Okay, and related to the calculation, right? You should know these 4 equations, right? If you have a vapor pressure, okay, then the vapor pressure can be calculated using the mole fraction of your solvent, okay, times the vapor pressure of pure solvent. Okay, so this is actually how you calculate the vapor pressure. Okay, this is actually how you calculate the freezing point depression, right? Delta TF, the change of the freezing point temperature is I times KF times M. Okay, and then the change of your boiling point will be I times KB times M. And then the osmotic pressure can be calculated using pi equals to I times MRT. Okay. So here, make sure that you know the R here, you need to use 0.082 ATM. Okay. So that's the things that you need to understand. Okay. So that's all the things that you need to know for chapter 10. Okay. So you can actually start to evaluate how much do you understand. If you like, okay, the things I say already know everything, then you're good. Just practice more questions. Okay, if not, then go back to watch the video. Make sure you actually comprehend the things I just said. Okay. That's not much, right? I finished everything in 5 minutes. Okay. So let's go chapter 10. Okay. Chapter 11. Chapter 11 is actually a lot of definitions. Okay. But once you know the definition, then you kind of like already memorize it. Okay. So in chapter 11, we start to talk about the reaction rate. Okay. So the reaction rate always have the unit of molarity per second, right? When we talk about a reaction rate, that's always the unit. Okay. But we later on also learn, okay, to actually write the reaction rate, you can write it from the disappearance rate of your reactant or the appearance rate of your product, right? So if I say calculate the disappearance rate of your reactant, then I'm actually talking about this term, right? Delta reactant concentration, delta T. That's the disappearing rate of reactant. If I say the appearance rate of product will be delta product over delta T. Okay, but none of these two terms represent your reaction rate, right? To calculate your reaction rate, you need to actually further normalize by its coefficient, right? And sometimes you need to actually further insert the negative sign so that the rate becomes positive. Okay, so you need to actually a very clear distinction between the overall reaction rate and disappearance rate of your reactant or appearance rate of your product. Okay, those are three different terms. So when you read the questions, make sure you know what's the things you need to solve. Okay. And then we start to talk about this differential rate law, right? Differential rate law always have this formula: rate equals to rate constant K, lowercase k, times reactant raised to certain power, right? So the power of that can only be determined experimentally. Yeah, so when we talk about chapter 11, we always have these big tables, right? You actually write out those equations and do this equation division type of things to figure out the orders of the reactants. Okay, so those are the things that you need to be really good at, okay? Then we also say for different order of reactions, okay, you can actually use the unit of your rate constant K to know what's actually the reaction order of the overall reaction. Okay, so remember the unit of different orders is important, okay? And this is actually just a general expression to tell you, okay, the N is actually the overall reaction order, right? So if you have zeroth order, first order, second order, you can just plug that in so you will know what's the unit of your K. Okay. And after that, we start to talk about for a single reactant integrated rate law. Okay. So you will have these three equations, right? For the zeroth order, you say the AT equals to negative KT plus A0. Okay. If it's first order, it will be natural log AT equals to negative KT plus natural log A0. Second order is 1 over AT equals to KT plus 1 over A0. Okay. So it's very standard. You just need to actually recognize it. Okay. And in your homework or in your quiz, right? Sometimes you see this plot. Okay. So if you see a linear relationship, okay, when you plot out the natural log AT over T, okay, if you see a linear relationship that tells you it is a first order, because that's actually the only thing that contains natural log. Okay, so all these three is actually linear equations, right? Where you can actually consider this is actually y, t is actually your x. You can consider this actually y equals to negative kx plus b, right? The same thing here. All the three equations, they are all linear relations. Okay, but just in different order, your y is different. Okay, but your slope is always k or negative k. Your intercept is always a0, natural log a0 or 1 over a0. Okay, but they are all linear. So what you're trying to do is actually looking for the plot that shows linear relationship and look at what's the y, right? If it's actually a of at, then zeroth order. Natural log at, first order. 1 over at, second order. Okay, so it's actually very straightforward. Okay, so that's actually the integrated rate law, right? And then you also need to know when we talk about the half-life time, that means actually at less specific time t, okay, the concentration of your AT will equal to 1/2 of your A0. Then we start to talk about how the kinetic rate constant K is related to the activation energy and the temperature. Okay, so K equals A times e to the negative EA over RT. Okay, so make sure you know the R here has to be 8.314. Okay, so that's actually different from the collective property when we talk about the pressure, we use 0.082, right? And if you actually start to see this keyword activation energy, you know the upper one is actually equation that you need to use. However, if you see inside the question, you start to talk about rate constant K at one temperature, another rate constant K in another temperature, right? Then it's actually time you to use the bottom equation, natural log K1 over K2 equals to EA over R, 1 over T2 minus 1 over T1. Okay, the order matters. Okay, don't mix these things up. So this will be actually all the things for chapter 11. Okay. But there's actually one more thing, sorry, forgot to mention. So the very last topic we talk about in chapter 11 is actually the elementary step, right? So if I give you the elementary step and tell you which one is actually the slowest step, right? Can you actually use step-on layer and derive the overall differential rate law? That's actually another type of question that we need to actually cover for chapter 11. We have an example like that today, okay? But that's pretty much all for the chapter 11. Then we come to the very last one, chapter 12, last week. Okay, we start to introduce you the concept of chemical quotient Q, right? So equation-wise, the chemical quotient Q and equilibrium constant K, they look exactly the same. Okay, differences is that you can only write K when the system is at equilibrium. Okay, so you can actually write Q at any given time point. Okay, then you should know that if you what does it mean? Okay, if the Q is actually larger than K, and it means actually you have more product than equilibrium states, right? That means actually you're wishing to actually move to the reactant side so that you have a chance to reach your equilibrium. Okay, equilibrium is actually the endpoint of all the reactions, right? So then whatever your Q is, your reaction need to actually move in a direction, make it look more like K. Okay, so that's actually a concept that you must have. And then depending on you use gas or solution to calculate your K, equilibrium constant K, okay? This two is actually interconvertible using this equation, okay? So Kp is equal to Kc times RT to the delta nth power, okay? So the delta n can be calculated by the gas molecule sum on the product side minus the gas molecule sum on the reactant side, okay? And then the very last thing we talk about, of course, we start to talk about this, right? And then we start to introduce the concept of ice table. Okay, so ice table, we practiced quite a few times last week, right? So make sure you know how to put a number in the correct rows. That's critically important. Okay, so make sure you actually practice that. Okay. Another thing is actually if I give you a equilibrium constant K for a specific reaction, okay, if we actually do some multiplication of the equations, can you calculate the new K? Okay. So for those calculations, it's very simple. If you flip the reaction, then you put the -1 power in the new K, right? You multiply X, then you put the X the same on the power of that new K. Okay, if you have two equations with equilibrium constant K1 and K2, if you add up those two equations, the new K will equals to multiply of these two original equilibrium constant. Okay, so those are the things that we talk about as for the completeness. Okay, right? You should know how to actually write out your ICE table properly, okay, and populate all the numbers in the correct rows. Okay, so that's all. That's all the things we teach so far for how many weeks? 4 weeks, right? So it's not a lot. Okay. But this is actually not a lot once you understand the content, right? But you need to actually spend our time trying to actually understand what it means in the past couple of weeks. Okay. So if you feel like you can fully understand what I say, that's very good. But if you're not, then really go back and watch my old videos. Okay. So I talk relatively slowly when we first time talk about the topic. Okay. So when you play the video, like play 1.5 times or 2 times, that can save you a lot of time as well. Okay. So any question for this? If not, we're going to go into the questions. We good? One more thing. Today, let's actually student come to my office and ask about like besides the things of my hangouts, right? What other things that you guys should do to further prepare yourself, right? So I told them that the ACS, the American Chemical Society, okay, they have the past exam. Okay, so it's actually the exam somehow students actually deposit into ACS. Okay. Everyone know where the ACS chapter is? It's in the Fleming building. Everybody know Fleming building, right? Yeah, second floor. Okay, so if you enter from the front door, okay, then turn right, you're going to see the stairs. Go to the second floors. Okay, turn left, then you'll see the ACS chapter over there. Okay, and just talk to them and ask them, okay, do you guys actually provide the previous CHEM1312 midterm 1 exam questions? Okay, ask for that. Okay, I think, I don't know how many they have, but I think many students actually deposit their questions over there. Okay, so get a set of 2. Okay, so purchase that too. Okay, and after that, what do you do? Yeah, so let's actually practice midterm 1. Okay, in the Cengage. Okay, so make sure you do that. Okay, so you really need to time yourself. Okay, so when you actually feel that I'm ready to take the exam, okay, then do the final test. Okay, so only you, your calculator, a few scratch paper, that's all you should have. Okay, and be honest with yourself. Okay, so I always tell my kids that one thing that's very important that we must learn is that we need to learn to be brave. Okay, so when I say we need to be brave, what does that mean? Because kids doesn't understand when I say, okay, what do I mean by brave, right? I said the first thing you do is actually be honest with yourself. Okay, you know what you know what you don't know. Okay, be really honest to your situation. Okay, you tie it, you have the data, respect the facts. Okay, and then once you actually actually inspect how you perform. Okay, if you don't do well, recognize it. Okay, trying to figure out what is actually things that you don't do well. Okay, and then change it to improve yourself. That's what I call brave. Okay, and actually recognize our flow. Okay, and come out a way to really address those things and make ourselves better. That's brave. Okay, so make sure you do the same. Okay, only you, your calculator, scratch paper, let's all. Yourself. Okay, you have 22 questions. Yeah, 22 questions for midterm 1. And you have 75 minutes. Okay, so make sure you actually finish, then you can actually go back and recheck all the answers that you have. Okay, so you need to be really fast. Okay. All right. So if you can do all those things, I think you will be fine. Okay, but get back to here. Let's start from reading the questions and write out our QD pack. Okay. So if you see this question, it says determine the mass in gram of cyclopentane. which they give you the chemical formula and the formula weight, okay? That must be added to 60.3 grams of benzene, again, the formula weight and the chemical formula, to make 0.599 m of solution. Okay, so what is the keyword here? Yes. But you need to practice this a lot, okay? Right, let lowercase m is molality, right? That's where you know the equation that you must use is what? M equals to moles of your solute divided by mass of a solvent in kilogram, right? So let's actually the first thing that you should see, because once you see that if you have less salt, then you know you already actually have a plane. Right? So it is very important that you recognize the keyword because they help you to really come to the equation really, really fast. Okay? Okay, so once you know, okay, that's the keyword. I know I need to use this equation, right? Then we read the question trying to figure out what is actually things that you really need to solve, right? What's your Q? What's your Q? What's the things you need to solve? Mass of the solute, right? In grains, right? That's the things that you need to solve, right? Okay, then start to actually collect the data. You have C7H14, whose formula weight or molecular mass equals to 98.2 grams per mole. And then you have C6H6, formula weight is 78.1 grams per mole. And then you know the molarity have a concentration with a value of 0.599 m, right? Okay, do I have all the data here? I do, right? I should include everything already, right? So now the things I want you to think, okay, in a more general terms, you need to actually know what's your solute, what's your solvent, right? So what's your solute? Dichlorhexane is your solute. This will be your solvent. Is that correct? How do you know? Yeah, it says A is added to B. You see that? Yeah, A is added to B, right? Because solute is always being added to the solvent. Okay, so you should actually recognize the structure of the description too. Okay, that's how scientists describe the process scientifically. Okay, so things actually follow a very specific pattern. Okay, so you really need to actually learn how to read these things. All right, so with that being said, then the next thing will be the plane, right? Because we know the mass, the molality is going to equal to the mole of your solute mass of your solvent, right? Then you start to check what is the things that's known already. Do you know this term? That's actually 0.599, right? So you can write that. Do you know this guy? You don't, but you know the definition of that guy, right? So what's the definition of moles? Yeah, so the mass of your solute divided by the molar mass, I prefer formula weight, okay, of your solute. Do you have the mass of your solvent, which is? I should actually write out. I do actually make something. How come you guys cannot tell me? So solvent is 60.3 grams, right? So this will be 60.3. Okay. Divided by 1,000, right? Okay. So once I write up to this point, I realize I actually also have the formula way of my solute, right? Therefore, you know the bottom one is 98.2. Okay. So far, so good. Okay, so once you have this, look into this equation. How many unknown do you have? One, right? Is that what you want to have? Yes, right. So just solve these equations. Okay, using your calculator. Make sure you actually do these things correctly. Okay. So once you're doing all those things properly, then you should be able to figure out that the mass of your solute will equals to 3.55 grams. Okay, so this is actually a very standard type of questions. Okay, so if you have a correct concept, right, you recognize your concentration terms, you know your definitions, right? You list out all the things that you know, plug it in. Solving these things should be actually really, really quick. Okay, but that is based on that you can actually really see the keyword, know what equation to use. Then all these things will be very straightforward. Okay, so this requires you to practice a little bit more. Okay, now let's actually how you solve the question number 1. Okay, any question for this? I hope it's clear. Number 2. Calculate the vapor pressure in torr at 310 K in a solution prepared by dissolving 37.63 grams of non-volatile, non-electrolyzed sucrose have a molecular weight of 342.3 grams per mole in 129.7 grams. The vapor pressure of water at that temperature is 47.08 torr. What's the keyword here? Very good. Okay, so when we talk about the vapor pressure in the beginning of this lecture, right? How do you actually calculate that? The pressure is going to equals to mole fraction of your solvent times, right, the vapor pressure of pure solvent. Okay, so I know that's actually equation that I'm going to use. Okay, so I have planned already, right? Even before I actually dive into do my QD pad, I know what to do already. Okay, so this is the key. This is actually how you can just solve a problem within 1 or 2 minutes. Okay. Okay, so once I know my plan, right, then I go back to my QD pad. Okay, Q. Q is really trying to actually figure out the vapor pressure, right? But you need to have a unit of torr. Okay. Data. Okay, so temperature is 310 K. Okay, and then your solute, you have 37.63. And then the formula weight of that is 342.3 grams per mole. Your solvent apparently is water, right? And then you have 129.7 grams. Okay, and then the vapor pressure of your pure solvent is 47.084. Okay. So that's all the information I can pull out from the question. Okay. Now I can go to my plan. I know my plan is I can calculate the vapor pressure using mole fraction of my solvent times the vapor pressure of pure solvent, right? Apparently, this is actually the things you want to solve, right? To solve the P, then you need to have this and that. Okay. Do you have mole fraction of your solvent? You don't have that from the question itself, right? But we can actually know the definition of that is the mole of solvent divided by the mole sum of solvent and solute, right? Do you have this? The vapor pressure of pure solvent. It was given, right? It's this, right? So you know that's 47.08. Okay. Now we come back to this, right? Can we actually calculate the mole of my solvent and the mole of my solute? Right? So, and then this exercise that you need to know. I will just do it here, right? Because the mole of your solute will equals to 37.63 divided by 342.3. That gives you a value of 0.11. The formula weight of your solvent, which is water, right? H2O, you should be able to calculate that. Okay, formula weight is 18, right? So the mole of your solvent will be 129.7 divided by the 18. You got 7.21. Okay. Once you have that, then what you need to do is actually plug this back in. Mole of your solvent is 7.21. Mole of your solute is 0.11. And you do this calculation, you're going to get a value of 46.37. And that will be your answer. Okay, any questions for this? It's very straightforward, right? It's really, okay, trying to find the keywords. Once you know the keywords, you know what equation to use, right? Start to collecting your data from the question again. Write it out in a neat way, okay? Then start to plug in the things that you have, and then look at the things that you don't have yet to see whether you can actually do one more layer of analysis, right? So to know the definition of moles. If it does, then you can actually calculate those things, okay? And then if you do enough, you'll realize that by doing this, it's very easy to actually get to your answer. Okay, so let's see how you do your question number 2. Number 3, consider the solution 0.04 N urea, 0.04 N. Oh, before we go to this, I want to actually highlight a few things. Okay, I forgot to mention this actually earlier. Okay, so what does that mean? When you have things that's non-volatile, non-electrolyte. So when we talk about the vapor pressure, the default thinking is that only your solvent will contribute to the vapor pressure, meaning that your solute is actually just a solid. Okay, but if your solute is a solvent, then it will actually also contribute to the vapor pressure. Okay, but the things we talk about here is simple case. Okay, it's non-volatile, means that your solute is not going to produce any vapor pressure by itself. Therefore, all the vapor pressure will coming from your solvent, which is water. Okay, so that's why I have that word non-volatile over there. Okay. The second keyword it says is non-electrolyte. Okay, what does that mean? It means actually your Van Hoff coefficient equals to 1. Okay, so it's very important you see this. Okay. What if the solute that you have is an electrolyte? Let's say your solute is an electrolyte. They have Van Hoff coefficient of 2. Then what do? When you calculate that mole of your solute, okay, you get the number, right? That's actually a molecule, right? But once they dissociate, they become electrolyte. Okay, you need to actually multiply 2 on that when you're plugging into the final equation. Okay, everybody follow what I say? You see this is how we calculate the mole fraction of your solvent, right? So it's mole of your solvent divided by the mole sum of your solvent in solute, right? So this is true when you have a non-electrolyte, meaning that it doesn't further dissociate. Your solute, if a one solute molecule wants to dissociate, you still have one molecule inside your water. Okay, but if today you store in your solute, it is an electrolyte, meaning that it's storing 1 mole, but it produces 2 or more particles. Okay, if you use sodium chloride as example, I equals 2, right? If storing 1 mole of your sodium chloride, but you're going to produce 2 mole of solute particles, right? Which is 1 Na plus, 1 Cl minus. Okay, if that is the case, then the mole of your solute particle, this one need to actually multiply that Van Hoff coefficient, so I can get the correct answer. Okay, even though I haven't seen any questions involve that concept, okay, but that's if you encounter some more challenging questions in the future, that's something to be careful about that. Okay. All right, so question number 3. Consider solution. Okay, you have 0.04 m urea, 0.04 m AgNO3, 0.04 m calcium chloride, which has, first question, highest osmotic pressure, lowest vapor pressure, and then highest boiling point. What are the keywords here? What are the keywords here? Right? So every time you see osmotic pressure, vapor pressure, boiling point, freezing point, those are the terms that you know is testing your collective property concept, right? So collective property concept is very simple, right? You need to calculate the effective concentration, which is your Van Hoff coefficient I times the given concentration, right? So when you have a higher effective concentration, you know you're going to have lower vapor pressure, lower freezing point, and higher boiling point and osmotic pressure. Okay, so those are the things that you need to know. Okay, so once you have those concepts, okay, so the Q says I want to have the right. These are the 3 things that you need to solve, right? So the one has the highest osmotic pressure is actually the one with the highest effective concentration, right? Everybody get this? Okay. Lowest vapor pressure. Also the highest, right? Highest boiling point. Yeah, apparently it's all highest, right? Everybody fine with this? It's very simple analysis. If you have the correct concept that you know, you're actually looking for the highest effective concentration, right? So after this very simple analysis, you should know that the answer for the three things should be the same, right? Sometimes you just look at the options, so you already know the answer. Okay, but we need to actually do our data, right, to see what's the things that we have. We have three species, right? So you want to calculate the effective concentration, right? Which equals to I times the molarity, right? What's I for your urea? 1, right? So how do you know it's actually 1? Yeah, if you look at the formula, all you have is what? CHO and X, right? It's pure organic compound. It's not strong acid, it's not strong base. Okay, so it's not an electrolyte. Since it's actually not electrolyte, therefore I equals to 1. Okay, how about the second one? AgNO3, 2, right? So the reason it's 2 is because here you should know some of the polyatomic anions, right? So NO3 minus is actually something that you need to actually memorize. Okay, and then therefore you know this one will be Ag plus. Okay. So the reason I write Ag plus here is because on the left-hand side of the arrow is neutral, right? There's no charges. Overall, net charge is 0. Okay, that means on your right-hand side, the net charge also needs to be equal to 0. That's why I write Ag plus and NO3 minus, right? 1 plus, 1 minus, they cancels out. It's neutral as well. Okay, and then since you have 1 cation and 1 anion, therefore you got 2 solute particles. All right, so that's why you get 2. How about your CaCl2? 3, right? So CaCl2. So Cl always carries -1 charge, right? That's, I always say 7A elements is always -1 charged. Okay, once they dissociate. Okay, you have 2 of them. And then calcium 2 plus, okay, it's actually a 2A element. Once they dissociate, it always carries +2. Okay, since I have 1 cation and 2 anion, therefore your I equals to 3. Okay, so once you know this, then you can calculate your effective concentration. This is 1 times 0.04. Still give you 0.04. This will be 2 times 0.04. That give you 0.08. This will be 3 times 0.04. That give you 0.12. Okay, so from here, you should be able to see that the CaCl2 is actually the one that have the highest effective concentration. Okay, therefore that will be the answer for all three. Okay, so let's actually how you address this type of questions. Okay, any questions? We good? Can I move to the next one? Okay, question number 4. Tin chloride dissolved in water according to this specific equation. What is actually a boiling point of solution when 0.2605 gram of tin chloride is dissolved in 10 gram of H2O? The Kb of water is 0.512 degrees C per milliliter. What's the keyword here? Boiling point, right? Very good. And then boiling point tells you this is the collective property, right? Then you should know that delta Tb, the change of boiling point is actually I times Kb times m. That will be the equation you're going to use. Okay? So once you know that, then you have plan already, right? Then start to define your Q. What's your Q? The final boiling point, right? The final boiling point of the solution is the things that you want to solve, right? And then you should also know that this TB will equals to the original boiling point of, let's call it normal boiling point of your solvent, in this case is H2O, plus your delta TB, right? And the normal boiling point of your water is what? 100. That means actually the final TB will be 100 plus your delta TB. Okay? And then you want to calculate your delta TB using I times KB times N. Okay, so let's actually things into calculate. Okay. Then you can start to collect the data, right? So you have this specific equation. What's your I? 5, right? Because you produce 1 tin 4 plus and 4 Cl minus, right? Totally 5 ionic species. Okay, I equals to 5. Okay. And then your solute. Okay, so you have mass of your solute equals to 0.2605 gram. The formula weight of your solute is 260.5 grams per mole. And then your solvent is 10 gram, right? And then your Kb is equals to 0.512 degrees C per molality. Okay, so those are the things that you should be able to pull out from the questions. Okay, so once we have all this information, okay, then we know we can calculate final boiling point using 100 plus your delta TB, which is I times KB times M. Okay, so we know the I is 5, KB is 0.512. Do you have molality here? You don't, right? Therefore, you have to write out the definition of your molality, which is the mass of the mole of your solute divided by mass of your solvent in kilogram, right? Therefore, you know, this will be 100 plus 5 times 0.512. To calculate more of your solute, you will know the mass of the solute divided by the formula weight of the solute, right? So there will be 0.2605 divided by 260.5. That's how many mole of solute that you have. Mass of your solvent is 10 gram, but to convert into kilogram. Okay. So by doing that, you know this will be 100 plus this whole thing. You push your calculators, you should be able to get a number of 0.256. Therefore, you know your final temperature is 100.256 degrees C, right? So there will be the final boiling point after you dissolve all this solute into your solvent. All right? Next question. Okay, so when 5.66 of unknown non-electrolyte is dissolved in 50 grams of acetone, the boiling point increased by 3.8 degrees C. If the Kb is 1.71 K per molarity, calculate the molar mass of unknown solute. Keywords, boiling point, right? Therefore, you know this equation you're going to use. Okay? Q, what's the things you want to solve? The formula weight or molar mass of your solute, right? That's the things that you want to solve. Okay. Then start to look at the things that you have. You know your delta TB equals to 3.8 degrees C, right? What's your I? How do you know it's 1? Non-electrolyte, therefore I equals to 1, right? Because it says non-electrolyte. Okay? And then you know your Kb is 1.71 K per molarity, right? And then what do you know else? You also know the mass of your solute is 5.66 gram, right? Mass of your solvent is 50 gram. Okay? Everybody can pull out this information yourself. Okay, so once you have all these things pulled out, right? Then you know your delta TB is equals to I times KB times M. TB is 3.8. I equals to 1. KB is 1.71. Then you want to actually calculate your molality, right? Apparently you don't have lab, but you know the definition of your molality, which is actually the mass of your solute divided by the formula weight of your solute over the mass of your solvent divided by 1,000 to become kilogram. Okay. Here you see that your data tells you the mass of your solute is 5.66. You don't know the formula weight. You know the mass of your solvent is 50 divided by 1,000. Right? Okay, so therefore we know 3.8 is going to equals to all these things, right? Yes.
I'll say it's over or
Yes. So do you need to actually change the A to C? Do you need to? Okay, so the answer is actually no. Why? Because change of 1 degree C is the same as change 1 degree K, right? The difference between C and K is just the offset, right? K is C plus 273. But here, actually, you don't calculate the absolute temperature. You calculate you want to know the differences. So that offset will cancel out. So it doesn't really matter you calculate K or C, they are the same thing. Okay, make sense? All right, so since here, the only unknown is actually the formula weight, right? So you can just solve your formula weight and you should be able to get the number of 51. Okay, and that's actually what you're trying to solve, right? The formula weight of your solute. That's how you actually get to this. All right. Next questions. Calculate the molarity of an aqueous solution that is 8.1% by mass calcium chloride. you might need to know the density is 1.1 gram per mole. Okay, what are the keywords here? Molarity is 1. Percent by mass, right? That's the mass percent, right? So you see two concentration terms, therefore you know it's a concentration conversion questions. Okay, that means actually you need to make some assumptions to make your denominator equals to 1 or 100, right? So molarity is capital M, right? Mole of your solute divided by volume of your, or just liter of your solvent, right? Yeah, I always use this. Volume of your solution in liters, right? Mass percent is mass of your solute divided by the mass sum of your solute and solvent times 100%, right? So those are the two equations that you will need to use. Okay. So Q, apparently you want to calculate your molarity. Okay. And here you also mentioned the density, right? Should you use the information of density in this calculation? Yes. Okay. Every time you have a term called molarity, you are going to use the information of density. Okay. So let's write out the data that we have. The data is actually your mass percent, okay, equals to mass of your solute divided by the mass sum of solute and solvent as 100%, right? This equals to 8.1%. Okay, and then the density is 1.10 gram per milliliters. Okay. Here, what's your solute? What's your solvent? Okay. Your solute is calcium chloride. Solvent is water. Okay. How do you know your solvent is water? Okay, so the keyword here, aqueous solution, right? Therefore, you know your solvent is water. All right, so those are all the information you get. Okay, then we have plane, right? So the plane is what? The known concentration is your mass percent, right? Because your mass percent equals 8.1. Therefore, what you need to do is actually assume the denominator, which is this, right? Mass of your solute plus mass of your solvent equals to 100 gram. Okay, so here we use 100 instead of 1 is because you need to actually multiply 100 afterward, right? So they will cancel out. That's why we actually assume it's 100. Okay. So if it's actually 100 gram, then it means the mass of your solute is 8.1 gram. The mass of your solvent is 100 minus 8.1. That's 91.9 gram. Okay, so this is actually H2O. That's your calcium chloride. Okay. Once we understand this, right, the next thing we want to know is actually we want to calculate this, the molarity, which we need to know the mole of your solute divided by the volume of your solution. Okay. The mole of your solute is easy to calculate, right? Because the mole of your solute can be defined as the mass of your solute divided by the formula weight. The mass of your solute is 8.1 gram. And then the formula weight of calcium chloride, the formula weight, if you check out the periodic tables, you should be able to calculate the formula weight is 110.98 gram per mole. Okay, therefore, you just divide by 110.98. Then you can get the mole of your solute equals to 0.073. Okay. Then you have your numerator solved. The next step you need to actually solve is actually your volume, right? So this actually we're going to use the density. Okay. So density was defined as the mass of your solution over the volume of your solution. Therefore, you know to calculate the volume of your solution, going to do is actually the mass of your solution divided by the density of the solution. Okay, so the mass of the solution, which is the mass sum of your solvent and solute, right, which is 100. Okay, and the density is 1.1 gram per milliliter, right? So when you do this calculation, you got 90.9 milliliters, therefore equals to 0.0909 liters, right? I simply divide by 1,000 to convert the milliliters to liters. Okay, so once you have all this information, then you just plug this in. So you have 0.073 divided by 0.0909. Then you can get your molarity equals to 0.803. Okay, so that's actually how you get to the answer. Okay, so this is actually very standard concentration conversion type of questions, right? So you start from the two concentration terms, okay, know their definitions, okay. Then start from the non-concentration, make the appropriate assumption, which make your denominator equals to 1, okay. And starting from there, trying to figure out what are the terms that you need to calculate the molarity, okay. So we still have 2 minutes left. Let's finish this one. The next questions. Okay, so this question is actually relatively simple. So this question says, KBr does not dissolve well in nonpolar solvent because of what? Okay, so it's going to give you a lot of options. Okay, but when we talk about the solubility, okay, the things that you should start to think about is the interaction between the solute and the interaction between solute and your solvent. Okay, so KBr apparently is actually electrolyte, okay, and is hydrophilic, okay. Nonpolar solvent means actually organic solvent, okay, that means actually hydrophobic. So you know your solute and solvent, they don't like each other, okay. So in that case, you will say the interaction between your solute, okay, which is solute-solute interaction, are stronger than the solute-solvent interaction. Okay, so this is actually your delta H solute, right? And this is actually your delta H mixing, right? So you can say this statement, okay? Another statement you can say is that the lattice energy of the solute is much larger than the solute-solvent interaction, okay? Because here the solvent is actually not water, right? But if it is water, then you say the lattice energy is larger than the hydration energy. So those are the terms that you may actually encounter for this type of questions. But again, it comes back to you need to know, okay, is the solute-solute interaction stronger or solute-solvent interaction stronger? Okay, so that's actually what I want to cover for question number 7. We're trying to finish all the remainings on Thursday, okay?